Hello everyone, this is Vijetha, Associate Professor in the Department of ECA from MLR Institute of Technology. Today I would like to talk on converters using IC741 from linear and digital integrated circuits. We have current to voltage converters and voltage to current converters. First we will see voltage to current converter. Here this is a circuit which provides a voltage to current converter. That is, it produces an output IL in terms of V in. For converting a voltage signal to a proportional output current, there are two converting circuits. First one is voltage to current with a floating load, and the second one is voltage to current with a grounded load. Voltage to current converter accepts an input voltage and gives an output current which is IL. Voltage at node A, let us assume the voltage at node A is Vi. Therefore, IB is equals to 0 and Vi will be equals to IL into R1, that is, IL can be given as Vi by R1. This shows that the input voltage Vi is converted into an output current IL, since the same current flows through a signal source and load. The signal source provides this load current. The voltage to current converter using a grounded load. Here the load has been grounded. Now, let us assume the voltage across the positive terminal is Va and the current across this is approximately equals to 0, and Va is the voltage across a negative terminal of an op-amp. And RL is a load resistor where you will be finding out the load current IL across the RL, and RF is the feedback resistance, the current through RF is I2. And R1 is the input resistance, the current across the R1, let it be I1, and the input voltage given to the circuit is Vi. Now, from this circuit, across this node, if you can apply a KCL, you can write the current entering across the node is I1 and I2, which is equals to IL. So, here you can write an equation I1 plus I2 is equals to IL. Now, I1 can be given as this Vi minus Va, the voltage across this node A, let it be Va. So, you can write Vi minus Va divided by R1. Let us assume the resistors which we are considering here are equals to some value which I am assuming it as a R. So, you can write I1 as Vi minus Va divided by R, and I2, the current across this I2 can be given as V0 minus Va divided by RF, where I am assuming R1 is equals to RF is equals to R. So, you can write this as V0 minus Va divided by RF. Now, let I1 is equals to Vi minus Va divided by R, and I2 is equals to V0 minus Va divided by R, which is equals to load current IL. If you can solve this equation, you can write it as Vi minus Va plus V0 minus Va is equals to IL into R. The denominator part, which is R, is taken to the RHS side. So, you can write this expression as Vi plus V0 minus 2Va is equals to IL into R, which is written here. Vi plus V0 minus 2Va is equals to IL into R. Now, this expression can be given in terms of Va as Vi plus V naught minus IL R is equals to 2 VA. So, VA can be given as VI plus V naught minus IL R divided by 2, which we got here. VA is equals to VI plus V naught minus IL R divided by 2. See, as the input voltage is given to a positive terminal, that is non-inverting terminal of an op-amp. So, V naught, and we have a resistive network here, so it is not possible to apply directly, as V naught is equals to 1 plus RF by R1 into Vin. So, here we can write V naught is equals to, we can write here from this arm, we can write V naught is equals to 2 into VA. 1 plus RF by R1 into VA. Let us assume that RF is equals to R1. So, you can write 1 plus R divided by R. So, we got VA is equals to VI plus V naught minus IL R divided by 2. As this circuit, if you can see this circuit has been connected as a non-inverting amplifier. That is, VI is connected to a positive terminal of an op-amp. So, the gain of an op-amp can be given as 1 plus RF by R1. The gain is nothing but ratio of V naught by V in is given as RF by R1. So, you can write this V naught is equals to 1 plus RF by R1 into V in is the voltage across node A, which is VA. So, finally, you can write V naught is equals to 1 plus RF by R1 into VA, where I am assuming RF is equals to R1 is equals to R. So, which you can write V naught is equals to 2 into VA, such that you got V naught is equals to 2 into VA. But we have determined VA as VI plus V naught minus IL R divided by 2. Substitute this VA across this V naught is equals to 2 VA. You will be getting an equation as VI plus V naught minus IL into R. So, now we got an equation as V naught is equals to VI plus V naught minus IL into R. Here, if you can look at this positive plus V naught, it cancels out and we can write VI is equals to IL into R. So, VI is equals to IL into R. If you can write this in terms of load current, because as this is voltage to current converter, you need to get output current in terms of input voltage. If you can rearrange this equation, you can get IL is equals to VI divided by R. 1 by R is nothing but a transconductance, so you can also write it as IL is equals to VI by G. So, finally, transconductance GM can be given as IL by VI, which is equals to 1 by R. This is about voltage to current converter, that is, we are getting output current in terms of input voltage. The next one is current to voltage converters. Here, you can have inverting current to voltage converters and non-inverting current to voltage converters. In this, first we will talk about inverting current to voltage converters. A current to voltage converters, or we will call this as an ideal current controlled voltage source, which is also called as a trans resistance amplifier. The output voltage is equals to a constant K times the magnitude of the independent current, which is I here. The output voltage is independent of load connected to it. The constant K has a units of ohms. Due to virtual ground concept, the voltage across VA will be equals to VB, which is equals to 0. The current through R1 will be equals to 0 and II flows through the feedback RF as V naught is equals to minus II into RF. In order to reduce the high frequency and the possible oscillations, a capacitor CF has been connected parallel to the RF. So, current to voltage converter, the output voltage in terms of current. So, here we got V0 is equals to minus II into RF, output voltage in terms of input current. The next one is non-inverting current to voltage converter. The input current II have a written path to ground over here. The voltage at a non-inverting terminal is given as Vi is equals to II into Ri. As input voltage is given to a positive terminal, non-inverting terminal, we can write V0 is equals to 1 plus Rf by R1 into Vin, where Vin is II into Ri. So, finally you can write V0 is equals to 1 plus Rf by R1 into II into Ri. That is output voltage in terms of input current. Here we have discussed about voltage to current converter, and we also discussed current to voltage converters. Voltage to current converters, that is IL in terms of input voltage, we have determined it as a transconductance. So, we got load current in terms of input voltage, IL is equals to Vi by Gm, voltage to current converter. And coming to current to voltage converters, we have inverting current to voltage and non-inverting current to voltage. In inverting current to voltage, we got V0 is equals to 1 plus Rf by R1 into II into Ri. We got in terms of non-inverting terminal, whereas in inverting terminal we got V0 is equals to minus II into Rf. Thank you.